This is Pre-Calculus, Chapter 8, Lesson 1, Introduction to Vectors, and we're going to start out by doing the definition of a vector. So here we go.
Hey! I'm applying for a new villain loan. Go by the name of Vector. It's a mathematical term, a quantity represented by an arrow with both direction and magnitude. Vector! That's me, because I'm committing crimes with both direction and magnitude. Oh yeah! Check out my new weapon. Piranha gun! Oh yes! Fires live piranhas. Ever seen one before? No, you haven't. I invented it. I'm doing a demonstration. Oh! Ah! So difficult sometimes to get the piranha back inside.
Mr. Brew, Mr. Perkins.
So a vector is something that has both magnitude and direction. The magnitude and direction can be represented in so many different ways. We're going to go through and do some examples, but it could be how hard you push on something, how far you go, how fast you go, and the direction can be represented many different ways as well. So we're going to go ahead and look at that. So to start with, back in Chapter 5, you use trigonometry to solve triangles. That would be sine, cosine, tangent, SOHCAHTOA, if you had a right triangle. But if it was not a right triangle, then you also used the law of sines and the law of cosines. And you'll be using all of those in this section. So if you don't remember the law of sines or the law of cosines, you'll need to go back and review those before you can do the homework on this section. So what we're going to do now is represent and operate with vectors geometrically. And when I do this, I just basically estimate and approximate. The book is going to say use a compass, use a ruler, use a protractor, and I don't do it that way. I don't know what your teacher is going to ask you to do, but I would normally estimate geometrically, and then as we go further into this section, you will solve vectors using the trigonometry and get the vectors into their rectangular components. You don't know what those are yet, but that's okay. We'll get to that. Okay, new vocabulary. There's a lot. Vector. Something that has magnitude and direction. Since a vector has magnitude and direction, it has an initial point and a terminal point. Think of it like a line segment, which has 2 points, and the arrow is on the end point, so you know which direction you've gone in. And we're going to draw tons of vectors here in this lesson, so you'll get used to seeing that. But the initial point is where you start, terminal point is where you end. A vector in standard position is where the initial point is at the origin. And if you're going to be able to work with vectors using trigonometry, you will have to be able to put them in specific places in space so that you can understand their relationships. So you have direction, magnitude, and then you have a few different ways that you can represent the direction and the magnitude. One is called a quadrant bearing, one is called a true bearing, and we'll get into those. Parallel vectors are just vectors that are parallel, just like parallel lines. Now, if a vector is going north and another vector is going south, those are still parallel. They're just going different directions. An equivalent vector would be two vectors that are exactly the same. They just might be in a different place. Opposite vectors. An example of opposite vectors might be going 10 miles north and then going 10 miles south. So if you add opposite vectors together, you end up where you started. A resultant would be when you add vectors together, and we're going to be doing quite a bit of that in this section. As a matter of fact, that's what most of your homework is. And the way that you find a resultant, there are two methods, the triangle method, the parallelogram method. I only use the triangle method. I will introduce you to the parallelogram method, and for me, the parallelogram method is just more work, and It is no more accurate, just more work. If you want to use the parallelogram, you can. That's why I introduced it to you, so you can decide, but I will tell you that I use the triangle method exclusively. Okay, zero vector. What do you think the magnitude of a zero vector is? Right, it's 0. And it's important to have a zero vector because direction can be important. If you're standing in one place, you're not moving, so your magnitude would be 0. But if you're facing north or if you're facing east, that can be a very important thing to know. So there is such a thing as a zero vector. It has a magnitude of 0, but it has a direction. Components are just when you break a vector down into 2 or more parts. And you'll see through some examples where that comes in handy. And then rectangular components, that is when you break a vector down into 2 components that are at right angles. And specifically the ones we're going to deal with is break a vector down into its x and y components. And that's, in section 2, we're going to do a lot more with rectangular components, x and y components. And you will see that rather than using geometry to do this, when you can use your rectangular components, the problems become much less complicated. Okay, so let's do some examples here. If you have a hockey puck and you shoot it northwest at 60 miles an hour, is that a vector or a scalar? Now, to be a vector, it has to have magnitude and direction. So in this example, you have magnitude of 60 and direction of northwest. So there are many, many, many ways to represent direction. There are a couple standard ways that direction is used, and we will cover those, but anything that represents a direction, up, down, left, right, northeast, southwest, anything like that, anything that represents a direction can indicate a vector. So here's the second one, serving a tennis ball at 110 miles per hour. Is that a vector or scalar? And remember, to be a vector, you have to have magnitude and direction. In this case, you have magnitude, you do not have direction. It doesn't say what direction you served the tennis ball. Therefore, this is a scalar quantity. Okay, last one here. State whether a sprinter running 100 meters north is a vector or scalar. For a vector, you have to have magnitude and direction. And for this, you have a magnitude of 100 and a direction of north. So this is a vector. Okay, guided practice for you. Go ahead and give it a shot. I'm giving you the answer in 3, 2, 1. That is a vector because you have a magnitude of 100 newtons and a direction of due east. Okay, so representing a vector geometrically, you're going to draw a vector that is 10 newtons at a force of 30 degrees to the horizon. So at this point, let's skip over and take a look at what that might be like. So here we go. There are 3 basic ways to represent vectors that you'll be using in this chapter. There are other things like northeast, southwest, and so forth, but basically you'll be using 3 different ways to represent it. This is the problem that we were just looking at. If you are above the horizon, the positive x-axis is the horizon, and then you go up from there. Another way to measure is going to be something called quadrant bearing. So this example here, you would go south 70 degrees west. So that would be south 70 degrees west. Now you could also say west and then how many degrees south? So how many degrees would this be? That would be 20 degrees south, because from south to west is 90 degrees. So if this is 70 That's got to be 20. So you could say west, 20 degrees south. With quadrant bearing, by tradition, you always reference within one quadrant. So it's going to be south, how many degrees west, or west, how many degrees south. And you'll never get up to 90 because west, 90 degrees south would be south. And you also don't cross over into other quadrants. So you wouldn't say south, 110 degrees west. While technically, you could draw a vector based on that, by convention, quadrant bearing, you start with one of the sides of your quadrant and move towards the other one, but you stay within a quadrant. And the third way that you'll see in this section is something called true bearing or just bearing. And that is from north, going clockwise, all the way around until you get to 359 degrees. If you got to 360, you would just be at 0. So there aren't, in any of these, there are not the concept of coterminal angles. Because it's just a direction, you want to write it in the most easily understood method. So true bearing, it just gives you how many degrees from north going clockwise. Quadrant bearing, you would start north, south, east, west, and then go whichever direction you are in that quadrant, however many degrees, and then say what direction you went. So that's just a quick breakdown of the 3 different ways that you'll see vectors referenced for direction. Okay, so now we're back at this representing a vector, 10 newtons at a force 30 degrees to the horizontal. And because it says 30 degrees to the horizontal, that would be 30 degrees above the horizontal. It might say below, and then it would be, if it said below, it would be down in this area down here. And because there are so many different ways to represent direction for a vector, you have to read the problems carefully and understand what they're saying. Okay, now this one says 25 meters, so that would be your magnitude, south 70 degrees west. So with this, you would go south and then you would rotate 70 degrees to the west and draw the magnitude of 25 meters. And again, for me, I just do sketches. I wouldn't do a scale. I wouldn't make you do things precisely in this particular effort because we're going to move very quickly into using trigonometry to solve these. And with trigonometry, you can be very precise based on a sketch and a little bit of math. Now the next one, 10 miles per hour at a bearing of 025 degrees. Now it might say true bearing or just bearing, and this sort of a reference is used for things like navigation. In airplanes, ships, that sort of stuff, you would give your heading and it would be in true bearing. So 25 degrees from north going clockwise. And then the magnitude again would be 10. And they give the scale of 1 centimeter is equal to 10. Depending on what you're looking at this on, it may or may not be 1 centimeter long. I don't get hung up on that. Okay, give this one a shot. Give you the answer in 3, 2, 1. And the answer is C. And the reason that it's C is bearing of 80 degrees. So from north, you go 80 degrees. And that's kind of all there is to drawing vectors. And if you'll notice, all of these vectors are in standard position where the initial point is at the origin, and then the terminal point is out at the end of the arrow. And that gives you the sense of direction, and the magnitude tells you how strong it is. So the next thing we're going to talk about is adding vectors. And remember, I said the triangle method is what I use and parallelogram method is not. So in the triangle method, you take one vector and the second vector and you put them nose to tail. And the way I like to think about it, if you start at the beginning of A, travel down A, and then travel down B, and you end up at this point. Now the resultant is you start at the beginning of A, and you end at the end of B. An example of this might be if you are in a city and you walk 2 blocks north and 2 blocks east, how far are you from where you started? And so you would go north and then east, and if that's where you started, that's where you would end. So that's the concept of adding vectors together. Now, the parallelogram method, you put the 2 tails together, like they did here with A and B, and then you make another copy of vector A up here at the end of B, you make another copy of B at the end of A, and then they both start at the same place, and they end over here. So really, to me, you go beginning to end of A, beginning to end of B, or you go beginning to end of B, beginning to end of A, you end up at the same place. So you've done the triangle method twice, is the way I think about the parallelogram method. For some of you, it might make sense, but for me, it's just easier to do the triangle method. And just like addition of numbers, it does not matter if it's A plus B or B plus A. So you can add the vectors in any order. So let's look at some examples of adding vectors. So you have a hiker. Shelley walks 2 kilometers north, 30 degrees west, and then walks 2 kilometers directly east. How far and what quadrant bearing is Shelley from the camp? Now, because it said what quadrant bearing, that means you have to use the nomenclature for a quadrant bearing. So let's go ahead and look at this. Okay, I have translated this over here. So the red vector is in standard position, and we're looking at 30 degrees west of north. So this is 30 degrees. And then due west, and both of these have a magnitude of 2. Okay, so I'm going to erase those directions for a second. There are a couple of ways I can do this. I can put go vector A and then vector B, adding them together, and if I do, the resultant vector is going to be the nice green color there. But let me show you, if you have B and then A, you get the same resultant vector. So let's see if we can figure out what's going on here, and I'm going to do it that first way that we had it. We'll go here and here. Because this is due east, we know this is perpendicular right here. Since we know this is 30 degrees, we know this is 60 degrees. Since this is 60 degrees, and both of these sides are 2, we have an isosceles triangle. That means both base angles are the same. If both base angles are the same, and this is 60, both base angles have to be 60. Interior angles of a triangle equal 180 degrees. 60 plus 60 plus 60 is 180. So what we really have here is an equilateral triangle. We have an isosceles triangle that just happens to be equilateral as well. So if the angle between the red vector and north is 30 degrees, the angle between north and the green vector is 30 degrees. So the resultant vector is 2 kilometers north, 30 degrees east. That would be the ultimate answer to this question. So let's step through and see how the book chooses to solve this. So they've drawn both vectors on a separate axis, and I would draw them both on the same axis initially just because it's easier. And then after drawing them on the same axis, they would use the triangle method. And they happen to do it the same way I did it the first, and then the second, and the resultant. And their triangle looks a lot more like an equilateral triangle than mine. And again, I sketch. And the reason that I sketch is it takes too much time to be perfect, and I want to use trigonometry to get an exact or a very precise answer rather than drawing and trying to measure with a ruler and so forth. So the parallelogram method, again, if you look up here, you have one triangle. And down here, you have another triangle. So you've done the triangle method twice. Again, might make sense to you. It does not make much sense to me. Start, finish. And then if you were to draw these out and do a precise protractor, rulers, all that sort of stuff, you would end up with 30 degrees in 2 centimeters, and you would say 2 kilometers north, 30 degrees east. We solved it using trigonometry and just understanding triangles, and did not have to precisely draw it. Okay, next example, orienteering, which is nothing more than walking around out in the woods with a compass. If you walk north 80 degrees east for 150 feet and then walk 200 feet due east, how far and what quadrant bearing is Miguel from his starting position? Now, what I want to do is take a look at this, and we're going to look at it in a little bit of a different way here. So north 80 degrees east at 150 feet. So that would be something like that. And I'm not sure why I got 2 there, but I did. So that would be your first vector. And then we'll do a second vector, which is 200 feet due east. So 200 feet due east. And then when we connect those two, do you see how your answer has to be between 80 degrees and 90 degrees north, 80 to 90 degrees east, and the magnitude has to be pretty close. If this is 150 and this is 200, it's going to be just a little bit less. Oops, wrong way. It's going to be less than 350. So we're looking for a number a little bit less than 350 with an angle between 80 and 90 degrees. So as we look at our possible answers, it's not going to be 37 degrees. It's not going to be 47 degrees. 80 degrees, it has to be more than 80 degrees. So 86 degrees and just under 350 feet. So A is the only answer that makes sense. Now, we could have gone in and used the law of cosines to figure everything out. And we'll actually do a couple of examples where we have to use the law of cosines. And you'll find that it is a very cumbersome, time-consuming way to solve problems. And in the next section, after you've gone through the cumbersome ways to do it, we will show you some easier ways to solve the same problems, but you have to understand the concept of vectors before you can do that. This looks like absolute value of v. Because v is bolded, that means it's a vector, and rather than absolute value, that means magnitude. So the magnitude of vector v is actually what that is saying. So k, or the magnitude of k, would be the scalar. So if you have a vector that has a magnitude of 10 and you multiply it by 2, so let's say a student walked 10 miles due north. If you multiply that by a scalar, you might say, and the next student walked twice as far. You would take that vector and multiply it by 2, and I forget what I said. So if it was a student walked 5 miles due north, the next student walked twice as far, that would be 10 miles due north, or 5, which is the magnitude, times 2, the scalar. So you would take whatever vector it is and double it. If k is a positive number, you're going in the same direction. If k is a negative number, you're going in the opposite direction. So if a student went north 10 miles, the next student goes the opposite direction twice as far, that would be south 20 miles. So that's basically the concept of taking a vector and multiplying it by a scalar. You're only impacting the magnitude. And if you want to say you're impacting the direction when you multiply it by a negative, but you're going the exact opposite direction, so the vector is still parallel, just going the other direction. Okay, so we're doing some geometry again, just drawing vectors. So a minus 3b. First thing you would do is take b multiplied by negative 3, so you draw it the other direction, and 3 times as big. So here it is the other direction, 3 times as big. So this is negative 3b, that's b, and you have a. So if you're going to add these together, you just move a up, a, negative 3b. The resultant vector goes from the initial point of a to the terminal point of b, and that new vector in green is a minus 3b. And I believe your homework, you'll have to be drawing some of these, and again, I estimate them. So as long as you are relatively close, showing that you understand initial point, terminal point of a, to the initial point, terminal point of negative 3b, and then connect from the initial to the terminal. And the way I always think of vectors is if I went for a walk, and I walk this direction for a while, and then I walk this direction for a while, the result from my starting point to my ending point, you can just draw a straight line, and that would be the resultant vector. That's the way I think about it. You might have other ways to think about it. Okay, you get to guess on this one, and I do not like this problem because there are 2 answers that are kind of both okay, but not really. So I'll give you a couple of minutes, a couple of seconds. Show you the answer in 3, 2, 1. They say the answer is D. I would accept C also. And my problem is N and N look the same, but M and 2M also look the same. And in this one, if the shorter n, if you've scaled down the shorter n, then maybe this is the 2m. But this goes back to the whole scale thing and the sketch thing. I would accept C or D as a correct answer if you were doing a sketch or an estimate. Okay, here is where we're going to get into a little bit of craziness. So you have an airplane flying at 475 miles an hour at a heading of 070, and you always use all 3 digits on the heading. It's never a heading of 70 degrees. It's 070, 001, whatever it might be. You always have 3 digits, and that's the way airplane pilots talk, and everybody wants to be an airplane pilot, so talk like an airplane pilot. Okay, so the airplane is going on a heading of 070, and there's a wind blowing from 120 degrees. So the first thing you have to do is draw those 2 vectors. So, and because you're just drawing it from north, they don't have an east-west line. They just start from true north, 70 degrees from true north, so 070, 475 miles an hour. And then the wind is blowing from 120. So you go down 120, and since it's blowing from, you have to put the point at this end, so initial and terminal. So setting up the vectors is absolutely key. And as we go through and solve this, it's very important that you do 2 things. First, you have to show your work. And second, your work has to be neat. And as we step through how this problem is solved, you will see why that is the case. Okay, so you have 2 vectors. You need to find the resultant vector, so you need to add them together. And by the way, in aviation, this happens all the time because you have a direction and a speed that you're going, and there's always wind. And if you don't take the wind into account, you don't end up in the right place. So the first thing we're going to do is we are going to draw the vectors, use the triangle method to draw the vectors. And let's go magenta. So you have the direction of the airplane and then the direction of the wind. And you notice initial point, terminal point, initial point, terminal point. So you can draw G, which is the actual ground track of the airplane. Now, you have two sides. You need to find the third side. And what we can do, if you go back to the previous diagram, this angle is 120. And I'll change pen colors here. This angle is 70. So the angle between them is going to be 50. And alternate interior angles are parallel lines, so you're going to have a 50-degree angle here. So what you really have is a triangle where you know two sides and the included angle. So if you know two sides and the included angle, you use the law of cosines to find the third side. So we're going to go ahead and do that. And using the law of cosines to find the magnitude of vector G. So c squared is equal to a squared plus b squared minus 2ab cosine c. Here are the numbers that you would put in. 80 squared, 475 squared minus 2, 80, 475. Cosine 50, make sure your calculator is in degrees. And then you come out with a really long equation, 428. So our units, I believe, are miles per hour. So the ground speed of the plane is 428 miles per hour. If we go back, 475 was the actual speed, the airspeed. And let's go back and look at that triangle. So it looks like the wind is not only blowing you to the left, but slowing you down as well. So it makes sense that the ground speed is smaller than the airspeed based on the geometry. Okay, now that we have found the ground speed, we need to find the angle. Using the law of sines, we can find the other small angle. And once you find the other small angle, which is 8.2, then it's 70 minus 8.2 or 61.8. So what was the little angle that we found? Let's go back and look at this again. So what we did, we moved the wind up here. Alternate interior angles, we found this angle to be 50. Once we had this angle at 50, we used the law of cosines, two sides and the included angle to find the third side. Once we had all three sides, we could use the law of sines to find the small included angle. Once we found that small included angle, and we knew this larger angle was 70 degrees, it was 70 minus that small angle, 61.8. So I hope what you've seen from this example is if you do not show your work and you do not write neatly, you will not be able to solve these problems. Which angle are you talking about? Where is that angle? What am I really trying to find? And this is just one way to solve this. If you wanted to find the third angle, there are just many ways to go about solving this. On almost all of these problems, you will first use the law of cosines to find the magnitude. Then you will use the law of sines to find one of the included angles. And then you will use your diagram to relate that included angle to either true north, if it's a bearing, or if it's quadrant. You will find where it is in space, and you'll have to go ahead and calculate that and figure it out. So here is one more problem. It's multiple choice. Jamie's rowing your boat due east at 20 feet per second, going directly across a river. And the current is going 4 feet per second due south. Find Jamie's speed and direction relative to the shore. Well, first off, if she is going due east being moved south, she's going to be in the fourth quadrant. And her speed is going to be greater than 20 feet per second less than 24 feet per second, just because of the geometry. So let's flip to the next screen. So here we are, 20 feet per second east, 4 feet per second south. And here's the incredibly awesome part of this diagram. That's 90 degrees. So how do we find the magnitude? We'll call this side C. C squared is going to equal 20 squared plus 4 squared. So C is going to be 20.4 feet per second. And 3 of our answers had 20.4 feet per second, so I'm pretty confident that is right. And that makes sense for the magnitude. Now, let's find this angle. Now, to find this angle, since we know this is 20.4, we can use sine, cosine, or tangent. But I'm going to use inverse tangent of 4 over 20, inverse tangent of 4 over 20 to get this angle, and that will be 11.3 degrees. So this is 11.3 degrees. So you could say 20.4 feet per second east, 11.3 degrees south. But it might also be 20.4 feet per second south, how many degrees east? So what would this angle be? It would be 90 minus 11.3, which is 78.7. So we're looking for 20.4 feet per second and either east, 11.3 degrees south, or south, 78.7 degrees east. Back on this slide, everything is south, so many degrees east. So 11.3, if it were east, 11.3 south, that would be right. That's not. I don't know where they get 29.8. So 78.7, south, 78.7 east would be the answer. If you didn't quite get that, go back and rewind, relook at it. But that's the work for that one. Okay, now we are going to start breaking components down into their x and y components. The great part about x and y is you don't need to use law of sines, law of cosines, because everything is a 90-degree angle at this point. If it's a 90-degree angle, you can use sine and cosine. So if, what is this, Will is pushing a shovel 630 newtons at 70 degrees, the magnitude is 630 newtons at 70 degrees. You can find x and you can find y. X, you would use cosine of 70 degrees is x over 630. Sine of 70 degrees is y over 630. So now let's break it down into its components. Cosine 70 degrees is x over 630. Sine of 70 degrees is y over 630. And it's magnitude. Magnitude of a vector in the x direction, magnitude of a vector in the y direction. So that's why it's written, looks like absolute value x, absolute value of y. It's magnitude x, magnitude y. So magnitude x is 630 cosine 70. Magnitude y is 630 sine 70. And get used to these equations, because for the rest of the chapter, we're going to be breaking things down into x and y. And it is magnitude of your vector times sine of the angle, magnitude of your vector times cosine of the angle. And that will give you the magnitude in the x and the y direction. So using your calculators, in the x direction, 215, and the y direction, 592. And it makes sense at 70 degrees that you would have a larger component in the y direction than in the x direction. At 45 degrees, it would be equal. If the angle is less than 45 degrees, x would be greater. So this says magnitude of x because is it positive or is it negative? Depends on how you draw your vectors and how you continue to do the work. So when they talk about horizontal and vertical components, there isn't necessarily a positive or a negative unless it is required within the problem you're given. Okay, this is for you to calculate. Soccer player kicks the ball 37 degrees above the horizon at 39 feet per second. So what is a vertical and horizontal component? I'll give you a minute. It's going to be less than a minute. Okay, pause the video to calculate it, and when you're ready, unpause. Give you the answer in 3, 2, 1. Okay, the answer is C. And if you think about it, the horizontal component needs to be greater than the vertical component because it's at 37 degrees. Since the horizontal component has to be greater, let's cross out the problems it can't be. Crossing out the problems it can't be, if I can figure out how to work the pen. The horizontal component is smaller than vertical, it's not going to be B. Horizontal is smaller than vertical, it's not going to be D. And so 28.75 and 23.28, you really have to do the calculations to make sure that you know which one is which here. And you can't really tell by looking, so you have to calculate those. Okay, that is the end of Chapter 8, Section 1. It was long. Remember, vectors have magnitude and direction, and there are many ways to add vectors and break them down into components depending on the types of problems you're going to solve. So there's some good review in this section for how to do some of the geometry, and we will get more into the trigonometry in the next sections.